would like to obtain a local universe from cosmological initial conditions. Of course, I'm not going to succeed as for example, Yuri has done it with, simulating very accurately the M31 and M3, but we are doing our best. Our M31 Galaxies is shown up there in the dark matter, in both CDM and wonder matter. Just an example of the kind of M31 we have here. Okay, so this is the people behind the CLUS project. CLUS project stands for Constrained Local Universe Simulations, and it's a collaboration between different institutions, Man University, Potsdam University, the Yuri University with Yehuda, Hoffman and a bunch of students there, and also Levin. And then, apart from these guys that were mostly involved in running, setting up the initial conditions and running the simulations and analyzing them, then there is a lot of other people that are interested in doing something with our simulations. So this is a list of some of the people. Of course, not all of them are listed here. But in any case, you can take a look to the CLUSproject.org, which is a web page where you can find most of the stuff I'm going to talk about here, animations and so on. Oops. Okay, so this is our CLUS builder. It's the famous Mare Nostrum universe. Mare Nostrum universe stands for because of the name of the computer. And so the computer was one of the biggest in the world when it was built. Unfortunately, it goes down now to 40th or even 50th in the world. But in any case, it's still one of the only computer which is located within a church. being in Spain, I think you can believe that it's a very Catholic country. So the only place to put a big facility like this one is within a church. Okay, so apart from that, we also have access to different other supercomputer resources from Germany and also from the CITA, which is the consortium of European supercomputers, and we got a fair amount of time there. And almost, in total, we spend more than 9 million hours in these simulations. Now, why do we want to do that? Is because, of course, we have the better observational data from the nearby universe because it's closer. And we want to do near field cosmology. We need to somehow try to beat the cosmic variance because the local universe is something that is not an average area of the an average volume in the universe, and so we know very well what are the distribution of matter around us, and if we want to compare the results from the models with the results from the local universe, then we need to at least simulate it in the most similar way. So it's getting from at the end of the day in our simulations getting more or less the same kind of mass distribution that we see in the real universe. Now, how do we do that? We use it the constraint simulation. So we just put constraints in the random Gaussian fields of the initial conditions, and to do that we just use the information, these observations from the forward for two different sources. One is to constrain the mass distribution. We just use the position of the X-ray clusters around us using Redshift and Bollinger X-ray clusters catalog, and also we put constraints using the velocity fields, similar velocity fields coming from the Mach3 and SVM. Now, so we can do that in different kind of cosmological models. And recently, we just have added the velocity fields from very short scales from the current Chensel data, which just represents the local volume, about not of the order of several megaparsecs from us. of course, these short scales, when we scale them back, so the idea is just to put these constraints into the Gaussian random fields in this way. So you just constrain a smoothing in a given smoothing scale, the density and the velocity field, and then you rescale. You just trace them back to the initial conditions of the simulation using linear theory. So the bigger the scale, the better the reconstruction method is. And of course, when you do the n-body simulations forward in time, then what you get is basically that the large scale structures are more or less well represented, but when you go to very short scales, they are basically random, because of course you cannot trust the linear theory back in time for short scales. So there is also a component of randomness in this kind of simulation, so you have to do many trials until you get what you want. Okay, so using this technique we have done lots of different runs, different volumes and different resolutions. Originally what we do is we just simulate a box of the order of 160 megaparsecs. This is the bigger box we have done it. In a 256 cube mesh, we put the constraints there, and then what you get here is this very fine, the typical picture of a simulation, but this time you can put names on it, because these are actual position of the objects, the real comma large scale. Oops. So this is a comma, this is the local supercluster, data cluster, this is spices and so on. And if we want to zoom in some of these regions, we just add more waves, more short scale wave, but all of them are just random. It's just random, completely random. So the only constraints are in the large scales.
How many constraints?
How many? Yeah. Depends how many clusters you consider. Depends on the box. You can consider as many clusters as you want.
Here, you consider 4 constraints, or
what?
Here, you're considering 4 constraints.
Oh no. These are just the objects. No, but there are plenty of I don't know how many classes are within this 80 megaparsec sphere around us. But there are plenty of them. I mean, what I look here is just the mass concentrations that you get at the end in the simulation. That they are in the positions where these objects in principle are in the real universe. Okay, then if we want to simulate, if we want to go look for a local group kind of candidates, then of course we have to reduce the scale, we have to increase the resolution. So we go to shorter, to small boxes, just basically getting the local supercluster here, Virgo and Fornax, and then with some luck trying to get one realization where a local group-like object is found. So just to see you, just to show you that the constraints work more or less. Here are two different realizations done in 2 different cosmological models, cosmological parameters, and well, if you look at the large scale distribution, they look pretty much the same. So they come from completely different initial conditions. So the constraints just force you to get at the end, the similar structures. Okay, so then if we want to simulate as I said, the local group, then we have to go to the smaller boxes. This is a 64 megaparsec box, and this is a 160. So you see that this kind of object is the same with the one we have here. Okay. Now, if we zoom in to this region, we found in one of the many realizations that we did, we found an object which looks very much like the local group, or similar to the local group. So in that case, we zoom in even further in a 2 megaparsec region with a maximum number of particles of 4096 cube, with the equivalent of having 4096 cube particles in the full box, which translates into a mass resolution of 200,000 solar masses. And this is the formation of this object. In the end, you will have like three main objects. Two of them we call them M31 and Milky Way because in terms of they are the most massive ones, and then there is another one nearby that we call M33 because of just a mass classification, nothing else. Like you see here, for example, this guy is going to be the Milky Way, this guy is going to be M33, and what we see from here is that we can infer what is the possible formation pattern of this kind of object situated as a binary system that is formed in an environment which is, you know, as better as possible, as close as possible as the real one. Okay, so I move forward. This is just another movie just to show you how it is formed in a you know CITA. This is the representation of the three objects here. As I told you, these are the two binary systems, and this is the other one that we call it M33 because of the mass. Another kind of local group object is found in a simulation of WMAP5, bigger object than in the previous case because we have a higher normalization factor here for the simulation. So the two objects are more or less at the right distance, and the masses of these objects are also quite close to the Milky Way and Andromeda. From all these simulations, we have done a lot of different kinds of analysis that I don't have time to just to comment on them. These are listed here. And for example, I just wanted to point out to the poster of Fabio that is in the coffee room about using these kind of simulations to study the annihilation of the gamma ray coming from annihilation of extragalactic sources. Something that is kind of new in this field instead of just focusing on the gamma decay of the galaxy. Okay, just let me point to how it works, just talking about what John was saying about timing agreement. Now we can have an idea what is, first of all, what is the velocity of these objects, how these objects were formed. So we see here that they form mostly in radial orbits, where the radial component dominates, and that they didn't have an encounter before, so they're approaching to the first phase center. So using that information, we can then compare what are the predictions of applying the timing algorithm to the different number of objects that we, local group kind of objects that we have found in the different simulations, and this is what you see here. And the interesting thing, I mean, we have identified many local group kind of candidates in all the simulations, and we have selected those which are, let's say, the best ones. They are sitting in the position next to the Virgo, to the right distance to Virgo. The other ones are just selected according to the circular velocities and the relative distance and so on. So we will see here those that are sitting in the kind of what we call the right position for the local group. They have a much better estimate of their masses as compared with an average local group object that you can find in a random simulation. And this is very interesting from my point of view. The point is why are these differences of the order of from a factor of 2 different between the mass estimate from the timing and the true mass? This is something that we are investigating. What is the reason for these differences? Okay, so I don't have time just to go through all the results. We also did that in Wonder Matter. We repeated these simulations in Wonder Matter to compare, to study different issues. For example, studying the abundance of satellites in the 3 different chaos that we found, and depending on the Wonder Matter mass of the particles, then we see a clear decreasing in the number of solid structures. We also did the same thing, but using the voids statistics of the local universe from the Galaxies data, and compare with our simulations, and we found that, of course, the land CDM have some problems in the sense that you can only reconcile with the number of voids that you can find in reality if you assume that your all the payloads with circular velocity less than 20 kilometers per second, they don't form stars. I mean, they're basically dark. Right? And this comes along with what Green was saying, the effect of photoionization in low circular velocity halos that will prevent them to form stars. Again, we have done the same another test with H1 galaxies in the local universe from the alpha survey. These simulations are very useful for that because we have more or less the same kind of distributions in the real universe, so the comparison should be done more reliably than assuming just a random realization. So comparing the Virgo and anti-Virgo regions, we found out that again the lambda CDM have a problem, have too many H1 galaxies as compared with what the alpha, the current alpha survey is predicting, and they won't have that much, give you much better agreement with the data. Okay, so I can go to gas dynamical simulations, but very fast. I mean, you can see all these animations in the web page anyway. So we did gas dynamical simulations of these local group objects, and well, what I can say is that we did found that in these dark matter halos we can form galaxies, spiral galaxies. The halos are like a factor of 2 less massive than the real ones. So the galaxies, if you look at them for example, for the luminosities of the galaxies using the Tal-Fisher relation, they are very well represented. They are very good. These galaxies, of course, much smaller than the Milky Way, than our galaxy here. But in any case, we do find these galaxies in this kind of objects, in this kind of environment. And using gas dynamical simulations and dark matter only, we can study different issues, like, for example, what are the effects of dark matter due to the baryons. The results are comes along with all the other simulations that do the same thing. They are not particularly interested in this case. The only thing is we have 3 halos simulated at the same time. The effect of adiabatic contraction, we also find that the typical adiabatic contraction models overpredict the contraction of the dark matter halos. They become more circular. Of course, this is also something known from many other simulations of this kind. The reduction of the number of substructures when you include baryons, just putting all the baryons, assuming all the taking all the substructures which are luminous, then you just reconcile with the number of satellites that you find in the Milky Way. And then finally, two new results that they are now in the process of referring. One is the direction of accretion of the satellites onto the Milky Way and Andromeda, and we found a clear signal that the satellites were not accreted in a random way, they are accreted in a preferred direction, which is the direction that is pointing very close to where the Virgo is. So there is a Virgo is here, so there is a filament connecting these guys with Virgo, so they are forming in these 2 filaments, and the satellites are preferentially aligned with that. Not only that, but also the matter strip from these galaxies, from these satellites, they also have this alignment, so they are not just mixed around, but they still keep this alignment with the original direction of the satellite when they enter into the first phase. And finally, the reionization of the local group, because we have Virgo, we have Fornas, we have the local groups. We can trace them back to the reionization epoch and try to see which were or who was responsible of the reionization of the matter that ended up forming the galaxy NM31. And this is unfortunately depends very much on the amount of the efficiency that you put in for the UV sources. If you put a photon-rich model, it means that the sources, the mini halos, are very efficient in producing UV photons. Then the local group was reionized externally, so the major the major source of ionization of the local group came from Virgo and Hornax, or from the progenitors of Virgo and Hornax. And if it is photopoor, then it means that the local group was reionized from inside. That is the bottom line of this analysis. And then, as I said, just let me conclude by saying that with this kind of simulations, we can try to address many different issues. It's a good laboratory to study many different issues, mainly because we can address, we can try to beat what in other situations you have to do is to try to do many, or try to find many objects that look like the local group in a random simulation. This time we do our best in order to model, or in order to find the structures that are as close as possible to the real ones. So, so thank you very much. And the cruise project, and then you will see.
So Yuri, why don't you come up? So while you're getting set up, maybe questions.
Gustavo, you seem to like the whole diagnostic simulations because they give you field loss compared to advanced effect.
No, I don't like it.
Well,
I just wanted to just compare.
I mean, these simulations are very tricky because you get lots of very curious numerics. It was spectacular. It seems like Bode and Ostreich. You see these lines of numerically induced loss. So what do you do about those?
Well, first of all, in the high resolution simulation, those blocks are very low. The fake powers are very small in mass and also in circular velocity. So all the results from
how do you know which ones are the fake and which ones are the real ones?
Well, I mean, you can follow, you can do it. I mean, the way we do it is just by fitting the mass function, the superstructure mass function. You see an uprising at some point, right? So this uprising means that everything beyond that is fake, because in principle the mass function should be flat. The cumulative mass function, the same way that Simon and Wang did it, just to come up with this formula. So we'll do the same. So we have pretty high resolution here, so we are confident that all the fake halos are not taken into account. We are well below our limits for the circular velocity. Or you can consider that these halos were first, at some point were fakes when they just formed in the beginning. Right? This is more tricky.
I think we better move on. This next time we'll get. So next is Yuri. Some dynamics of this. All right, good.
So I want to use half an hour or so that is given to me to briefly advertise two instabilities, right? So the first instability is one we have discovered and worked on, applied instability to eccentric disks, stellar disks, and galactic nuclei. Second instability is an old instability. It's Parker buoyancy instability, which we have considered in what we think is a different context, in the context of accretion disks. So let me just begin. Brief introduction. You all know that at the center of Galaxy, of our galaxy, there is a massive black hole. Such there it's a star. This is a cartoon of the environment of this black hole. So the black hole is sitting somewhere here. And if you look at the galactic center in an infrared, in the central parsec, you see a lot of very massive and young stars. So there is a starburst. And there are various indications which tell us that this starburst, the stars were born in situ, very close to the black hole. So it's a very unusual mode of star formation. And so the currently popular theory of, or at least the picture of how the stars are formed, is that they formed as a result of gravitational instability of gas right next to the supermassive black hole. And so in particular, Bonnell and Rice and other authors consider the following scenario, where they have thrown a dense clump of molecular gas onto the galactic center. So this gas then got tidally disrupted, formed an eccentric accretion disk around the black hole, but this eccentric accretion disk has fragmented into multiple stars. So this is the SPH simulations from Bennell and Rice, and all of these bright points. These are basically stars. And there are other people, other groups who have done similar simulations and have had a similar idea. So now, the question that I want to concentrate on today is twofold. First thing is I want to know what happens to the stars after they're formed. If they're formed with this geometry, it's certainly not an isolation, right? There is a cluster of spherical cluster of stars around this black hole, and I want to know what happens to the orbits of these stars. Okay, this is one question. The second question that I want to study and discuss is what happens. Now this simulation is pure hydro, right? Pure SPH hydro. What happens if this clump, if this molecular clump is initially magnetized? What happens if it has a strong magnetic field? How does the system behave in such cases? There is a good motivation to consider this because we know that interstellar medium is in fact strongly magnetized, and in particular galactic center has very strong magnetic fields. So let me just go straight to the core of the matter. This is the simulation of what happens to the eccentricity values of the stars which are formed in this eccentric accretion disks. And so all of the stars here are starting with eccentricity of about 0.6, right, which is basically taken from Bennell and Rice's simulation. Now what I have on the x-axis is time, right? What I have on the y-axis is 1 minus eccentricity. So the stars which are near the top are basically circular. The stars which are near here are basically on radial orbits, extremely eccentric orbits. Okay? Now it turns out, I don't have time to explain the details, but it turns out that the eccentricities of the stars in the nuclear cluster, if you immerse the stars in the nuclear cluster, they repel each other, right? So if you have a bunch of eccentricities here, it's equivalent to making a pile of marbles on your desk. Okay, so you make a pile of marbles. If you make it tall enough, what's going to happen? They're going to fly in all kinds of directions. The equations of motions which describe these marbles are qualitatively very similar to the equations of motions which describe the values of these eccentricities. Okay? And so you see these eccentricities, they fly in all kinds of directions. Some of them fly to low values, some of them fly to high values. And then there is some complicated dynamics which happens after that. But basically, the initial transient phenomenon is that there is a tendency for them to go in different directions. Let's look at the eccentricity vectors. Okay? So this is the eccentricity vector is basically a unit vector which looks at the periastron and has the value of eccentricity, right? So I start with a cluster of eccentricity vectors here. And you see how this cluster is going to dissolve as the simulation progresses, right? So you see it becomes stretched, and you see this beautiful tidal tail. Now remember, these are not actual stars. These are the tips of the eccentricity vectors. And you see that in particular, some of them reach very, very high values, and some of them reach very low values. Now let's look at the distribution of eccentricity, eccentricities that you get at the end of this simulation. So here it is. Now, this is the actual distribution that we get from the simulation. When I say we, I mean a PhD student, Henry Madigan, a postdoc, Claudius Hoffman, and myself. And this is the observed eccentricity distribution of the clockwise disk in the galactic center. And there is a suggestive similarity between these two distributions. In particular, there is a hint of bimodality in the data, and there is a certain bimodality that you see in the simulation, right? Because basically, these eccentricities, they fly in both directions. Now, this is as much as I'm going to pay attention to observations. So for the rest of the talk, I'm going to forget about observations, right? This is an institute of theoretical astrophysics, which means that there is a certain value of considering an abstract theoretical idea, right? And the abstract theoretical idea I want to consider is how do we fit supermassive black holes, right? And you all know that there is a problem in feeding supermassive black holes, in that typically if you try to do it, the gas, instead of being accreted onto a black hole, if you do naive calculations, say using alpha disk, the gas, instead of getting onto the black hole, fragments and forms stars. Okay, so this is a famous self-gravity problem. It seems that you can fix this problem if you do some of these three things, right? The first thing you have to do is you have to deliver the gas quite fast to the black hole's radius, right? The second thing which helps is if you actually move away from simple alpha prescription and you actually have some kind of accelerated accretion. If that happens, you don't linger around at the distances which are dangerous for gravitational instability. And the third thing which would help us is to have some kind of non-thermal pressure. Okay, now, most of the simulations, so galactic center story is suggestive. If you believe the story of formation of the stars, and you believe that there is some kind of, that nature provides you with gas clumps which get onto nearly radial orbits and fall into black holes. Okay, this is a big if. But if this happens, all right, then there are very few simulations of this process. And all of the simulations are non-magnetic, right? They just don't have magnetic fields in them. So I think magnetic fields will play a key role in this story. And at Leiden we have begun to investigate what happens to this type of in this type of process. And the two people who have carried out this research are postdoctoral fellows Yuri Gapurov and Anders Johansson. Now this is a very difficult problem. Okay, if you want to do a three-dimensional MHD simulation of a clump moving with highly supersonic velocity, interacting with a black hole, there is a variety of spatial and temporal scales. And this type of simulation is currently inaccessible to three-dimensional simulations. So what Yevgeny Gavurov decided to do, he decided to look at two projected problems, okay? So first you project and you make it a two-dimensional simulation in the XY plane. So in this simulation, you have a clump of gas, the black hole is sitting here, okay, and it's falling basically onto the black hole, and it does the Bonnell and Rice thing, it gets sort of tightly disrupted, you form eccentric accretion disk. Now, if you put a moderate magnetic field in here, okay, and you throw this clump onto the black hole, what happens is that magnetic field gets wound up by the shear, and it affects a very strong angular momentum transfer, and the disk that you form is much more compact, by almost an order of magnitude, than in the non-magnetic case. You can consider this problem in a different projection, right? So instead of considering this problem in XY plane, you can consider it in RZ plane. So go into cylindrical coordinates, make your cloud, your clump, spread it over into a torus, and then throw this torus with some angular momentum onto the black hole here. Okay, and just watch what happens. So what happens is that as this clump falls, you also generate very strong magnetic fields. They drive hydromagnetic outflows. So these outflows are shown in this direction. And if you look at the magnetization, right, so the picture of magnetization is shown here, you see that if you start with a moderately magnetic field, now so this is the color code here is a data parameter. Where it's green, it's actually super thermal, right? So the magnetic pressure dominates the thermal pressure of the gas. So when this cloud gets disrupted, you do get this outflow. But the point is that the large part of the disk has very strong magnetic field, very strong remnant field, which is left in the disk after this type of tidal disruption. This motivates a question. Now, what happens if you take a molecular clump, throw it into the black hole stretches this clump, tidally disrupts it, stretches into the disk, right? The magnetic field will stretch along, right? There is no time, because it happens on dynamical time, there is no time for magnetic field to escape from this. So let's suppose that we are starting that we now go and we say, let's suppose the disk has formed, and the disk has a strong toroidal magnetic field which has resulted from the tidal disruption of this clump. What happens in this case? So this problem was simulated by Anders Johansson in the shearing box approximation. Okay? So one thing that you may expect, and it did happen as a Parker instability. So what's shown here is the azimuthal direction along the x-axis and the vertical direction along the y-axis. You start your simulation with a toroidal field which is in equipartition with thermal pressure. So it's not particularly strong, not as strong as you get from the simulations of disrupting clumps. And indeed, you see this field becomes buoyant. There are magnetic bubbles which rise up. Okay, and material flows down, the field lines collects here. So you see how this instability develops in a non-linear way. Now, these are 2D simulations. And this is completely expected physics. Now, the unexpected physics happens in 3D when you put this situation in a shearing Keplerian disk. Okay? Now, the first diagram shows what happens if you have no shear, right? If you just have a sheet which has vertical gravity, but is rotating uniformly, so there is no shear. What happens in that case? Here I show the toroidal component of the field as a function of the scale. So z over h is the vertical coordinate measured in terms of scale heights of the disk. And you see that indeed the Parker instability does what it's expected to do. After 10 dynamical time scales, the field moves, the toroidal part of the field moves from the midplane of the disk all the way to the edges of the box. And if you run the simulations further, it basically fills the whole box uniformly. Okay, that's what happens, that's what you expect from Parker instability. Now what you don't expect, or at least we didn't expect, is when you add shear, this story does not hold. Okay? When you add shear, the field, essentially, it adjusts, but it remains confined very close to the midplane of the disk. Okay? So we have run this type of simulation hundreds of dynamical times. 2 minutes left. I'm almost done. And you can see that you get this field reversal. Okay, the toroidal field reverses direction actually in the upper layers, and this locks this locks the Parker instability. And we have checked that this is a real effect by, of course, enlarging in this direction. This is enlarging the vertical side of our box, and no significant change was noticed. Now, what is the interpretation of this? The interpretation, so this is an attempt of interpretation. I'm not saying it's a final version. But let's consider carefully what happens. So the first thing which happens is Parker instability. Material flows to here, to the bottom of this field line, okay? From the top to the bottom. Now, let's look at this field line from above, okay? Because the flow is converging towards the bottom, this field line is rotating this way, okay? Because the flow is diverging at the top, the field line is rotating the other way. So you get this type of helical spiral. I'm looking at it from the top. Now let's think what Keplerian shear does to this helical. So T stands for top, B stands for bottom. If you add Keplerian shear to this, the field at the top gets shrunk, okay? It gets contracted. The field at the bottom gets stretched, okay? And you see the field in the top is reduced, and the Parker instability is quenched, okay? So this is why the field is confined. Now let me show you the movie. Oops. This is the movie. And yeah, Anders is a very good computational physicist, so the movie goes on for 5 minutes. No, just kidding. You can see in the movie how the dynamo builds up the scale. This is the radial scale. This is the azimuthal scale. What's shown here in the color code is the vertical component of the field. You see the dynamo builds up the scale in the radial direction. The field becomes larger and larger scale. But it does remain confined to the midplane. So, in conclusion, what did I want to say in this talk? The first statement is that eccentric disk instability may be important in galactic nuclei. It may be even important in our own nuclear, galactic nucleus by setting the eccentricities of the stellar orbits. Okay, and it does support somewhat a picture. If you believe in this whole story of galactic center star formation, it does tell you that the galaxy finds a way to throw clumps at the black hole. Okay. Now, if you take this seriously, then strong magnetic fields are probable in a galactic etc. And they probably play a key role in the disk formation and dynamics. So that's it.
Okay, it seems like we're way behind, but remember we started 15 minutes late, so we're actually doing reasonably well. Quick question for Yuri. Yeah.
So do you expect that basically there tends to be a competition between the regimes where Parker is important and where MRI is important? If beta becomes too low, MRI should turn off. So I guess you have to worry about making sure that you don't pump too much field into the corona, turn off MRI.
So actually what happens is if you start with the horizontal field, as soon as you form a Parker bubble, the Parker bubble creates a very moderate vertical field. So this vertical field acts as a source of MRI. It's vertical field MRI. And that's not quenched. Whatever value of the field you take, even if you take a super thermal value of the field, the scale height of the disk will adjust in such a way that the MRI wavelength will fit in.
Right. Okay. So your results disagree with the kind of results that Blaze and Rosa and Krolik were finding, where they find a lot of carbon, they find a lot of flux being pumped into high altitudes. And
they start with completely different initial conditions, right? So they have zero flux, big field, and they build the field from completely different. What we argue is we're not disagreeing with them, but we argue that there is a second equilibrium, if you like. That it's possible to start with a very strong field, and then the dynamics of the system is completely different in this case. So that's all.
I think there could be plenty more questions, but I think I'd better move on. Yuri will be around.